Goa Science Project di ito'y kapwa kwatyo.
Iya, betong sami.
Di ho dan kwatige di ito'y kwatyo.
Ahya, tige topic wa be kilo. Wabe ho di kwa yahing. Ane, wabe twe hige.
There's a world so dangerous, so impossible, no one has ever attempted to explore it. It's not in space, not on Earth, but deep inside. We think we walk on solid ground. But traveling deep inside of our planet, we will discover another world. Filled with bizarre creatures that live only underground, we'll see gold formed before our eyes. Filled 120 degrees heat inside a volcano, discover diamonds buried 240 kilometers down, and giant tornadoes of liquid iron. Until over 6,000 kilometers down at the center of the Earth, we reach its beating heart.
Geology is the science devoted to the study of dynamic processes taking place on the Earth's surface and in its interior. As the primitive Earth cooled over eons, its interior separated into three major concentric zones: the core, the mantle, and the crust.
The Earth's interior consists of several different layers. First is the inner core, which is believed to be solid iron and which is very hot. Second is the outer core, which is believed to be consist of rocky material so hot and under great pressure that it is in a liquid state. The mantle, which is not as hot as the outer core and not as liquid. The mantle's outermost portion is solid. This is the solid outer portion of the mantle. Above this is the outermost layer of the Earth, the crust. Together, the crust and the solid outer portion of the mantle form the Earth's outer shell. They are referred to as the lithosphere.
We tend to think of the Earth's crust, mantle, and core as fairly static. In reality, convection cells or currents move large volumes of rock and heat in loops within the mantle like gigantic conveyor belts. We will be discussing about the Earth's tectonic plates.
Earth's crust. It is covered by vegetation and the oceans. But if you could drain the Earth's ocean and strip away our planet's vegetation, the Earth might look into something like this. Now we can see the Earth's outer shell, and if you could look closely, you can also see that the shell is cracked. The red glowing lines mark the places where the Earth's shell is cracked into tectonic plates. Each plate carries a continent or an ocean basin, or sometimes both. The plates are moving in an average rate of 1 to 2 inches a year in a variety of directions, carrying continents and ocean basins with them. Here's why the plates are moving. The scientists believe that the material in the mantle is circulating. The movement may be caused by heat within the mantle. You can get an idea of how heat can cause a circulating movement by watching rice as it boils. What you see happening within this beaker is similar to what's happening within the Earth's mantle. As mantle material moves perhaps only inches a year, it causes the plates above it to move as well. In some places, plates are moving in opposite directions. They are moving apart. The area where two plates are moving apart is called a divergent boundary. In other places, plates are colliding. The area where two plates are colliding is called a convergent boundary. And in other places, plates slide past each other. This area is called a transform boundary. This is a cross-section of a divergent boundary, the mid-ocean ridge, located beneath the Atlantic Ocean. The North American plate is on the left, and the Eurasian plate is on the right. Scientists believe that the plates move apart. Mantle material called magma rises to fill the gap. Magma is the name we give to a lava before it erupts from volcanoes as it is doing here. The magma cools and hardens on the ocean floor, adding new crust to old. And as the seafloor spreads, North America moves farther away from Asia. The highlighted area on this globe shows where magma is surfacing between plate boundaries beneath the oceans, creating a mid-ocean ridge that circles the Earth. The ocean floor spreads in one direction on one side of the ridge, and on the opposite direction on the other. The mid-ocean ridge is where the plate material is created. And this is where the plate material is destroyed, a convergent boundary. In this cross-section, the plate on the right is carrying an ocean basin and is moving in this direction. The plate on the left is carrying a continent and is moving on the opposite direction. The plate carrying the ocean basin is heavier and is diving beneath the plate carrying the continent. The leading edge of a diving plate is consumed back in the Earth's mantle. When one plate dives beneath another, it is called subduction, and the area where it occurs is called a subduction zone. Subduction may resemble what is happening on this lava lake, as sections of hardened crust dive beneath other sections. The highlighted areas on this globe mark convergent boundaries. Subduction is occurring at most of them. These are the areas where plate material is destroyed. Here again are divergent boundaries where plate materials are being created. Again, most of them are beneath the oceans, creating a mid-ocean ridge that circles the globe.
The Earth's crust consists mostly of rocks and minerals. A mineral is an element or inorganic compound that occurs naturally in the Earth's crust as a crystalline solid, or one that has a regularly repeating internal arrangement of its atoms. A rock is a solid combination of one or more minerals found in the Earth's crust. Based on the way it forms, rock is placed in three broad classes: sedimentary, igneous, metamorphic.
Igneous rocks, like this piece of granite.
Igneous means fire. This granite was created in a fiery place, perhaps long ago. Billions of years in the past, when Earth was new, there were no rocks. Earth was a burning hot, gooey ball of melted minerals and metals called magma. Eventually, as heat drifted into space, Earth's surface cooled. A crust of rock formed over it like ice over a lake in winter. This crust made of minerals and metals, cooled from red-hot magma, was igneous rock. Igneous rock is not only some of our oldest rock, it is also some of our newest. Earth has never stopped making it. Somewhere, people probably watch it warm right now at the edge of volcanoes. Lava is magma spilled out by a volcano. It hardens into igneous rock. Igneous rocks occur in many forms. They vary according to the kind of minerals and metals they are made of and how fast they cooled. Granite cooled slowly underground over thousands of years. Obsidian, which looks like black glass, cooled quickly, as did pumice, which floats in water. Though varied, all igneous rocks harden directly from magma. The second rock of our story is sedimentary rock. Sedimentary rock develops through a long process that starts with weathering and ends with lithification. Weathering breaks down rocks on Earth's surface through mechanical, chemical, and biological forces. In mechanical weathering, heat, cold, ice, wind-blown sand and falls slowly crack and wear down rocks. In chemical weathering, rock dissolves in rainwater, which is slightly acid. In biological weathering, plant roots both crack and dissolve rocks. Weathering occurs slowly, but old gravestones in cemeteries shows what can happen to exposed rocks. Over time, even huge mountains weather bit by bit into sand, dust, clay and minerals dissolve in water and disappear. 200 million years ago, The Appalachian Mountains were several times their present height. Where did the mountains go? They get carried away through erosion, wind, and especially water moves each bit of mountain rock downhill. Eventually, eroded rocks fill up nearby valleys or get carried away in a river up to the sea. We call the move material sediments. Wherever they settle, sediments accumulate in layers. In oceans, sediment layers may grow higher than our tallest mountains. Upper sediment layers press down the lower ones. These help lithification, the process that turns sediments into stone. Sometimes, layers get squeezed so hard, sediment grains get shoved into one another and lock into place. Other times, water evaporates from a layer and leaves behind minerals that glue together to tightly pack grains. Either way, what was once sand, mud, or gravel becomes sedimentary rock. Depending on how it formed, sedimentary rock may be quite hard, or rather, weak and crumbly. Sedimentary rock may not stay forever where it settled. Strong forces within Earth sometimes push rock from the bottom of the valley or an ocean into spectacular peaks along mountain chains. When sedimentary rock or any other kind of rock gets uplifted, it undergoes another cycle of weathering. Through same strong forces that push rock up may instead push rock down. If the rock gets pushed deep enough, it melts. Some future day, the melted minerals and metals may harden underground or erupt from a volcano to form new igneous rock. These storied third chapters tell us about metamorphic rocks. Metamorphic means change. Metamorphic rock may start as igneous, sedimentary, or even another metamorphic rock, but then somewhere deep underground get changed by heat and pressure. For example, limestone metamorphosis into marble, granite metamorphosis into gneiss. But once were flecks of black minerals are now stripes or layers of it. After knowing what the types of rock are, we will be discussing the interaction of physical and chemical processes that change rocks from one type or another is called the rock cycle. Rocks are recycled over millions of years by three processes: erosion, melting, and metamorphosis. Igneous rocks can be broken down through weathering, and the pieces can form sedimentary rocks. Igneous rocks can also change into metamorphic rocks when exposed to heat and pressure that change them but don't melt them completely. If exposed to high enough heat, they can melt back into magma to form new igneous rocks. Sedimentary rocks can break down through weathering to form new sedimentary rocks. They can also be transformed into metamorphic rocks through the action of heat and pressure. If they get hot enough, they can melt into magma to form igneous rocks. Metamorphic rocks can break down to form sedimentary rocks. They can also be converted into different metamorphic rocks when exposed to heat and pressure. Like igneous and sedimentary rocks, metamorphic rocks can melt into magma to form igneous rocks. As you can see, the interactions between the three main rock types can take several different paths, and any rock can turn into another type of rock with the right condition.
Bagong-bagong balita, tinas na ng PHIVOLCS sa Alert Level 3 ang Mayon Volcano. Ito'y matapos magtala ng kakaiba at madalas na paggalaw ang bulkan sa mga nakalipas na oras. Nai-record din ang may 39 na pagguho ng mga bato mula sa bulkan. Bukod pa sa 32 mahinang pagyanig, pinangabahan na rin ang posibleng pagbuga ng lava sa mga susunod na linggo. Dahil dito, inirekomenda na ang pagtupad ng 6-kilometer radius permanent danger zone at 7-kilometer extended danger zone sa southeastern portion nito dahil sa patuloy na landslide doon.
Recently, we've been experiencing worse calamities, both natural and man-made. And probably, for the next 3 to 5 years, we will be experiencing worse. We, the human beings, have caused this, so we can also solve such distraction we created. We cannot change the past, but we can definitely change our future, because we, as individuals, matter.
Some analysts say we have been asking the wrong question.
Instead of asking how we can increase supplies of non-renewable minerals, we should be asking how can we decrease our use and waste of such resources.
The available supply of a mineral resource depends on how much of it is in the Earth's crust, how fast we use it, the mining technology used to obtain it, its market prices, and the harmful environmental effects of removing and using it.
Here are some of the solutions that Meter gave to solve such problem. Find substitutes for some scarce mineral resources. Do not waste mineral resources.
Recycle and reuse 60 to 80% of mineral resources. Include the harmful environmental costs of mining and processing minerals in the prices of items. Reduce mining subsidies.
Increase subsidies for recycling, reuse, and finding substitutes. Redesign manufacturing processes to use less mineral resources and to produce less pollution and waste.
Use mineral resource waste as one manufacturing process as raw materials for other processes and slow population growth.
Small act, big impact.